All right, welcome to another episode of the Bioinformatics Lab podcast. I'm Kevin Libwit with Andrew Page. We're from Theogen, and today we're talking containerization, use and distribution of reusable software and all its impacts on the world of microbial bioinformatics. Andrew, I'm curious if you could start. When did you begin utilizing containerization, and how did it become kind of a best practice in your world?
I guess it's probably about 7 or 8 years ago. I heard about containers, and on the other hand, I was having terrible trouble installing bioinformatics software. I don't know if you realize back in the olden days, it would be quite difficult. You didn't have Conda, homebrews around, that kind of thing. It was just it was a mess. You'd have like Debian Med, which would be apt to get, but that's quite difficult to put stuff into. And so bioinformatics software was just a wild west, and trying to run anything was just a pain, and you might have people spending days and days trying to install software. And so my first introduction to it was just making containers so that other people could easily run my software and on their stuff. Because sometimes installations would be difficult, complex software, complex pipelines. You couldn't just hand them something and it would work. So that was my first introduction, was with Docker. And then I did some more complex systems. I think my first proper project was taking a very complex website with, client server, multiple backend servers, databases, all this kind of stuff. And then it was GeneDB, and then putting those into containers, and then doing kind of a Docker compose, to kind of spin the whole thing up, and have them all linked. And that meant that you didn't have to have all these complex things. You could have just these things you drop and they work.
Oh, that's interesting. I'm curious to get your perspective too on the website side, because that's where a lot of this technology kind of came from and more properly matured. And then we've co-opted it in the bioinformatics field for slightly different purposes. So we can kind of get into that. But maybe even, and you touched on some great stuff there with Homebrew. That's when I kind of entered the chat, was in the use of Homebrew and how to get things going. Then I learned about Python, or not Python, Conda, and all those package managers, and then containerization. Actually, before we start, maybe do you mind giving us a TLDR? What is containerization? Why is it important?
It is like a sandbox. In the old days, we had VMs, or we still have VMs,
Yeah.
which is totally disconnected from the base operating system on top. So it's like you're running Windows, you're running OS X or Linux, and then you have another operating system totally on top, and it's totally encapsulated, and it can't get to the main system usually. And Docker is much more, and Singularity are much more lightweight, and so they can reuse some of those bits. And it's not a very firm line; it's more of a soft, gentle line. A fence you can jump over if you need to. And so that's kind of what it is. And the idea is that you can spin these things up very quick. VMs are actually these big things that, it's like starting up, an old diesel engine, it kind of chugs along and it gets going and it warms up. Whereas, Docker is more like an electric car. You push a button and it starts. And so that's the kind of that kind of background. And the two major ones people use are Docker and Singularity. And there's minor differences. Singularity is more suited to, say, your traditional HPC systems, just the way it works and the way it kind of is slightly more secure. And then Docker is actually one that most people use, to be quite frank. And it gives you this beautiful system that you can log into it, or you can have one tool. My first interactions on a large scale with bioinformatics tools in Docker was actually on a cluster, your classical Slurm cluster,
Mm.
and they would load in Singularity containers for each tool, which is great. But building them and having them up to date is quite difficult. So what I did was I got a whole list of software, wrote a little script which would automatically build the definition files, config files, and from there that would create Singularity containers. And so, it was kind of automating this process of bioinformatics tool version, and then it would build it. And essentially, it was just getting Conda.
Yeah. Yeah.
So Conda, install tool, bang, there you go. And in 90% of cases, it would just kind of work. And which is great. And that meant a lot of tools were instantly available. Prior to that, someone would handcraft each file, and be tickets to IT, and there'd be all this back and
Yes.
forth and testing, and might be a week of work to get one tool put in, and I did 100 in an afternoon.
Yeah.
And that's kind of what people went and did, with biocontainers and things like that.
Yeah, and maybe we're kind of hopping over that step in the evolution of like best
Sorry.
practices in bioinformatics. From no, I totally hear that. From like hand installs, you were almost like, I think a lot of people came in, especially you're talking like 2014, 2016. Everyone was their own sysadmin. It's like we all had our own Linux environment, and then let's just install tools directly to the machine. And that's where it became really difficult because you had this, chaos of library dependencies that you were trying to manage yourself. And then you tried to run a tool that maybe, had to rely on Blast 2.3 or whatever it was, but then you have like three different Blast versions because other tools need different Blast versions. And it was like, how do you keep all these paths aligned? It was just chaos. It was just like untangling headphones that were like in your pocket for the day kind of thing. But I think what you said is appropriate, right? It's kind of separated from that base environment. So everything is self-contained that you need to run that resource. And it becomes um, unbelievably valuable, especially whenever you have very complex systems, exactly what you're talking about. And I actually got introduced to it whenever I was writing tools for the base applications. And it was not on my server, it wasn't on my machine. I had to load the software some way. And the way that they allowed you to do it was write a Docker image or create a Docker image. So even as I was approaching that problem, I was thinking, how the heck do I get all my library dependencies to run in this environment? And then I learned about Dockers and containers. I was like, oh, I can containerize all my software and it just exists and it pulls every time I launch the application. This is bananas. And then we immediately saw the utility across bioinformatics of there's that age-old problem of it works on my machine, right? Like, you see a paper, it's like, oh my gosh, what a beautiful software. It does everything I need it to do. And then maybe there's like, a supplementary section where it's like a markdown file on how to set up that environment with your local install. It's like, I can't get it to work. But then once it's containerized, it's like everybody can get it to work. So then that became just kind of like a light bulb moment in across microbial bioinformatics. And now what you're seeing is really common practice. Put a tool out, create the container.
Yeah. And so I even do that for testing. So if I'm giving you a project and it doesn't have a Docker, just to make it easier, before I modify anything, I will build the environment using Docker and put the software in there and try and install it from scratch because there's so many hidden dependencies that people don't realize. And it's only when you do that totally from scratch, you install a base Ubuntu, nothing else in there, and then you start going through, chucking through, what are these dependencies the developers have not written down, and you can very quickly tease these things out, and you get an exact specification for exactly how to run this tool. Super, super useful, and then it's contained, and everyone else can then reuse that, and they have a working environment.
Yes. Okay. So hopefully we've given enough of a preface and didn't lose too many people in the technical details on what containerization is and its utility in the field. Let's talk about the technical details a little bit because how you create a container or an image rather for people to use in their own environments. There's a lot of nuance in terms of how, what do you talked about base images as an example. How people write base images really will depend on its ultimate use case because there's some, especially in the world of like website deployment and things like that, their aim is to make it as lightweight as possible because sometimes they have Docker images that are getting pulled millions of times to serve all their different users and things like that. And even if you look in the bioinformatics world, this is true for things like the Nextstrain universe, where their Nextglade tool, they have very, 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 very lightweight Docker images with not even just like base Linux libraries. Like you can't do, if you launch one of their images, you can't even navigate the environment because it's so lightweight. It's meant to do one specific thing. Whereas if you look at maybe the StatB container images, we assume those are going to be run in workflow managers where you might do some file manipulation. You might need to do grep in between things, and they're a lot heavier because we assume people are going to need some of those base Linux or like Ubuntu package tools to navigate their environment there. So I'm curious what your perspective is, especially on the website side versus building tools and containers for other bioinformatics scientists for workflow managers.
Yeah, you're totally right. I mean, choice of base image is a difficult one. There are different camps. Some people use like Alpine, which is a
Yeah,
super lightweight
very.
base, which is great. But I personally always use Ubuntu or Debian, usually Ubuntu. Primarily because it works very easily and I know how to make it work. the other alternative would be using kind of a Red Hat CentOS kind of deal, that environment, and it's then that comes down to, how do you install packages. I like to use apt-get because it's straightforward. Other people, you can start with a base image of Conda. So you can take you've got layers, so someone can build, say, just a Docker which installs Conda, makes available, and then you can use that as your base image, and so you can layer these things on top, which is really, really handy for, say, standardization and things like that. Personally, my first step is usually I will get the latest long-term LTS Ubuntu,
Yeah.
and then I will install Conda, and usually it's copy and paste at that point. And from there, I'll do your standard apt-get update to make sure everything is actually updated, fix any key issues if there happens to be any, and then make sure the whole image is up to date. There's no security holes or anything like that. So basically, security patches, nothing else. And standard things I always install are like wget, nano, and
Yeah.
and things like that, because they're usually not there. And then if you're doing software development, you will probably need the build essentials as well. So that's compilers and stuff like that. If you're compiling, if you're not, you don't need to worry about it. And then from there, you go and do your stuff. And usually it's fairly straightforward. It's like copying the code from somewhere, maybe download from GitHub, or copy it in from the current working directory. And sometimes you have to set up certain permissions. Well, usually. And then at the very end you'd say, okay, well, this is a working directory, it's a command, that
Yeah.
is the entry point. And then from there you have it. So it's not that difficult. If you go into ChatGPT these days, it'll just tell you, I want to make this into a Docker, how can I do it? And goes
Yeah.
and tells you.
Yeah. And I would say uh Curtis Capsack, who's on our team at Theogen, and Kelsey Florick from the Wisconsin Public Health Laboratory, they wrote some incredible documentation on how to build Docker images in the StaffB Docker page. So we can link that in the description below. But I think you highlighted pretty much the base steps there. When you're writing a Docker file to create the image, you give your fundamental resources there, like you talked about, like you have an OS you start with, and then the basic tools for them to be able to navigate and do some basic compute, text management, text wrangling, and things like that. And then you get the tool in there itself. And then what you can often do is just follow the original author's instructions. How do you install it on a local system? Do you get it from GitHub? Does it need any other, library dependencies, as we spoke about? You just kind of stuff it all in there. And that is actually kind of an interesting point, because even if you don't know how to use or write your own Docker file, if you're getting your tool on GitHub, I can't stress enough how important it is to use semantic versioning and get version releases out, because that makes it a lot easier for somebody else to containerize your resource. You'll see in StaffB, we have like hundreds of tools we've containerized at this point, but some of those tools have authors that came from an academic background and not necessarily thinking, all right, I need to version control this and get this static. But it's like, man, it's such a useful tool that they developed as part of their thesis or something like this. But we want to make sure that it's a static version in the container. We don't want to just git clone the repo, because if they make a change, it'll be off that main branch. So we've come up with these funny tricks where we have to git clone a specific commit, and we think, okay, this is the stable commit. So that's what we have to do, especially during the pandemic. I remember that was quite common of an approach we had to do. Whereas if you had it as a stable release, a versioned release, okay, we know exactly how to name that. We can even make that a variable in the Docker file and just update it accordingly. And then from there, you're pretty much off and running. And that would be, you'd have a container there where people can use the intended tool, and then in their image as well, or in their container as they're running it, in their instance of it, they can interact with the files, they can add things, they can write their own code if they care to, add another quick bash script or something of the sorts, and then they're off and running, which is, again, not the case for all images. Alpine, I think that's actually the exact image that the next strain people use, because it's so lightweight. And it's sometimes surprising when you launch a really lightweight image and it doesn't have anything in there, and you're totally lost, because it's not meant, it's meant to do one thing very well a billion times. Whereas the images we're talking about it is meant to do that one thing, and potentially a couple of other things as well, like the text wrangling and maybe basic arithmetic or something like that. on top of
I
that
guess
one resource.
say standardization for a SAF-B, one advantage is you might have the same base image, and
Yeah.
then you don't have to re-download that each time. You know, it's already
Yes.
there and it's waiting, and you just kind of add the bits on top. And that's one of the real advantages of Conda, sorry, of Docker, is that you can do, you know, that the bulk of the work can just be there ready and waiting to go, and then you just add on your little extra tool on top of that. I actually do a lot of testing when I'm writing code. I would usually do it within the Docker container. So
Mm,
um, I will log into it directly. You don't just have to run the Docker command, you know, and run a command and get the results. You can actually log in and get a command prompt and do your work from there.
yeah.
And so I really enjoy that because it means that I absolutely know what the environment is, because I've spec'd it out. And if I make a mistake, I just delete and start again. You know, it's
Yeah.
a very, very quick turnaround in terms of what you're doing. And so I find that phenomenally useful. But one big question is always, you know, what do you include and what do you don't? Because a
Yes.
working Docker is can be quite different to the actual just pure base level installation, and particularly in bioinformatics where we have extra things we need to add in, like extra database and things like that.
That's a big point because yeah, we're talking about the size of the Docker image of someone versus Alpine versus using an Ubuntu, and that's already a discrepancy. But then the bigger conversation comes into, do you include a database? Because then you can really explode the size of your container, and it becomes a lot more difficult to ship. But if you sometimes with some images, it's not useful. There's no utility without the database itself. So that is always a kind of philosophical quandary we're debating back and forth, especially in the staff beat Docker admins, myself, Curtis Kapsack, Aaron Young, Kelsey Florick, and Kut Lujan from Connecticut. Do we include the database here? And that's always something tough, is because if you have the database, yeah, where do you land on database inclusion? We've had this conversation recently with even like the Gambit work we're doing.
Yeah, I mean, it depends. Like, it's a huge, it depends. If it's small, absolutely,
What
entirely,
is
you know, it's
small
not
in
going
your
to make any
mind?
difference. Small, oh, that's a good
Yeah,
question. Oh, I don't know. Like, you know, maybe a meg, you know, that's small. No one will
for
notice, you
sure.
know.
Yeah. Once you get in the
If,
gig status, it's like that's a different echelon.
when it's the gigs, that's the problem. And the big problem then becomes if if you have to pay, say in the cloud, you know, charges to download a 3 gig database, if you do it once it's fine, but if you do 1,000 times it's not fine, you know, that can be very expensive. Whereas if you have it within a Docker container, then that may be, you know, that'll be downloaded once and then it'll be reused, and you
Yeah.
don't have the extra charges coming in and out.
Cash. Yeah.
Exactly, yeah. And so you save a fortune then. And but if you're just doing it once, you don't save a fortune. So it's this kind of trade-off and balance. And you just have to be so mindful of that. People don't like big containers, particularly if you're running them not on the cloud, you know, you run them at home or on a laptop and that kind of thing. So you have to be so careful, and people are very passionate about it. But I think it's a very pragmatic thing. You can have the theoretical and the pure, and then you have
Yeah.
the, well, this is how it actually works in the real world.
That's a pretty good way to frame it. Where there's the purest thought of the most lightweight shippable containers versus how is this actually going to be used in different settings, and what is the most practical case of that. And the way we've solved it in staff B is we often offer both. We often, like, Kraken's probably a good one, Gambit's a good one, where it's like, hey, here's the super lightweight one where you can plug and play the database, especially maybe if you have it located or hosted locally on your environment or otherwise, or you want to localize the latest and greatest database, go for it. Here's that version, it's static there. If you're a laboratory that exactly what you said, doesn't want to incur all those egress fees or localization fees on the cloud because you're going to run it tens of thousands of times, and 1 or 2 gigs isn't bad at the scale of 1 or 2 samples, but 20,000 samples or something like that, especially daily, monthly, or whatever it might be, adds up fast. In that instance, here's that same image with the added Docker, or rather with the added database. And that is the beauty of what we're doing right now. It's like, we don't necessarily have to draw the hard line. It isn't that much more work for us to offer, to bifurcate to some degree and offer both there.
Anyway, we could talk about this all day, so I
Oh,
think we should
yeah.
probably go.
Yeah, forgot to put yeah, exactly. All right. So we'll see everyone in the next one.